Right, okay, good morning. So today's lecture, we've got, just to recap where we got to at the end of the last two lectures, we got on to convergence and divergence. Right? Convergence and divergence determine where you get vertical motion patterns in the atmosphere. And those vertical motion patterns determine where you get convection, and they also determine where you get cyclones and anticyclones growing. What I'm going to do in the last two lectures, the theory part of the lectures, is to develop this theme and to look at that from the point of view of vorticity in the atmosphere, which is a slightly better focused way of looking at the growth of cyclones and anticyclones. It's a little more direct than looking at convergence and divergence. But it's essentially the same thing, okay? So we're going to be looking at the same phenomena, but from a different mathematical perspective. I want to just start by talking about what we mean by growth of cyclones in particular. Today is a bad day to be talking about growth of cyclones because we've got a whacking great high pressure system. Well, there would be, of course, if I want to talk about cyclones, I'm bound to get an anticyclone. This is the Azores high, and it's basically pushed itself into our latitude. So we're due some pretty quiet weather over the next few days, probably some cooler nights, since obviously the nights are quite long now, and radiative cooling will be a factor. If we follow the forecast sequence, we can see this is tomorrow at midnight, so we can see midnight tonight, in other words, the very high. That's really quite high pressure. 1044 is pretty high. So the low pressure is quite a long way away. It's in this part of the atmosphere. What I'm going to show you is a forecast sequence of the growth of this feature here, which is just off the south coast of Greenland. It's not much of a system, this, but it is what's there. So if we follow it along, we can see it develops into this sort of pattern here. So we've got a cold front, we've got this warm front, so we've got a sort of region here which is the open wave, the warm sector as it's called. The air in here is warm, the air ahead is cold, the air behind is cold, and then we've got this kind of occluded front showing there. Occluded front is a front that doesn't reach the ground. And as we follow through it, it doesn't deepen very much, but you can see the warm sector is narrow. That's quite typical of these sorts of depressions. The occlusion becomes a little more prominent, and then it kind of fades away actually. The central pressure disappears, and and we're left with not very much. More interest perhaps is going back to this region here now. So looking in this region, this is the sort of birthplace of cyclones generally, and we're looking at the next set of cyclones again around the UK. By the way, towards the end of the week, we're looking at this feature here coming through. The air behind this cold front, you can see these isobars going all the way back to the Arctic. When we get fronts like this, with a fair bit of the pink in the isobars here, when we get one of these coming through, it induces a change in temperature. So if that comes through, as it's forecast to do, it's going to get quite a bit colder. So that's probably the same time, isn't it? That's midnight Thursday. So that's the same it's a forecast for the same time from the previous run. There's the front having gone through. But what you've seen is this frontal system here develops and goes up into the Davis Strait. Okay, so that's what the surface chart tells us. Well, we know full well that when we look at surface charts, we only get a small part of the picture. The reason we look at surface charts is they have these fronts on them. So let's look at this one. This is the upper air chart that we use. And so we have, at the moment, we have sort of northwesterly flow in the upper part of the atmosphere, and not surprisingly, given what we've learned before, this is a region where downward motion and therefore anticyclonic build up in the atmosphere and near the surface, and that's where this anticyclone is. So we've got this northwesterly branch of the jet stream. We would expect to see some cyclonic activity over this side, but that's not happening. Instead, we've got the cyclonic activity over here. And as we move forward in this sequence fairly quickly, there we go, that's a full day, that's midnight tonight, and as we can see this little low pressure, which eventually ends up with this thing around Greenland, and we can see this warm, so this is the warm sector, this warm, the cold front is of course showing us there's the temperature gradient here, this is the warm front showing us the temperature gradient. We don't really see the occlusion in this particular front, this system, because it's quite a weak system. As we come through, we can see the cyclone coming past Greenland towards Iceland, and again you can see the warm sector there tilting over, and then the whole system dissipates. So by now, this is Thursday, there's not a great deal over here. There is a new system starting off in this region, which is consistent with the downstream part of the trough. In fact, there's another one over here. But looking at this one, so keep your eye on the left-hand side of the diagram as I flick through these. So now we're starting to see, there's the growth just north of Newfoundland here of this, and what you can see clearly, it will be this tongue of warm air being drawn northwards. Okay, so you're going to see these warm colours being pushed northwards, and that's very typical of the development of a cyclone. And there's the warm tongue here coming northwards. That's the occlusion in this system. So this shows up as an occluded front. And basically that's what these cyclones are doing. They're basically taking warm air from the south and pushing it up towards the north, and it's a way in which the atmosphere is moving heat from the equator to the pole. The general circulation is trying to move heat from the equator to the pole. It's got a slight problem, the Earth is spinning. Because the Earth is spinning, there's a very strong Coriolis force trying to stop it from moving heat from the equator to the pole. It can't do it directly in the tropics. We can manage it in the tropics, but then at the edge of the tropics you get these very strong subtropical jet streams. And in these latitudes it manages it by spinning up these low pressure systems that push lumps of warm air, and you can see one here, there's another one up here on the right hand side of the diagram. So these are plumes of warm air that get dragged into the polar regions. This is actually very important for the disappearance of the ice, or this time of the year, the reluctance of the ice to reform. And there's been a particular issue, you wouldn't say off this chart, but in this part of the ocean in recent years, north of Norway, the Barents Sea, where pretty much the ice is not coming back. Parts of Svalbard, which is long the way north, which is top of the diagram there, that's Svalbard. Svalbard has been ice-free for the past few winters, which is not good news really. As we follow this through, you can see again the whole thing kind of dissipates, and you can see this large cutting off Rossby wave pattern, and that's basically the cold air that we are going to experience. So here we go, looking up over the weekend, you can see this blue colour coming over the UK here. That's really quite cold air. These are temperatures that are cold enough to bring snow. So I should think in the Scottish mountains over the weekend they may well encounter some snow. Not here, but and then it continues. So to summarise then, if I go back to this is a set of cartoons. This is from the web page. There are basically two paradigms of the way that cyclones evolve in the atmosphere, and these show the two paradigms. So this is what you'd see on a surface chart, and it's pretty much what we saw, particularly from this second example. They both actually follow this pattern, but you start off with this small kink in the polar front and small low pressure. The low deepens, and as that happens, this warm sector here narrows, and you get this plume of warm air, which is what this represents, which of course extends further following this occluded front as these two fronts merge to the left of the occluded front. And that's what these lines here are isotherms, so they're intended to show that There would be the colours if I'd coloured them. So you can see this. This is the plume of warm air. And in fact, if you follow it on the right surface, you can see that these things start to often curl around. So that's, and both of those things I showed you today, particularly the second one, followed that kind of paradigm. We don't have the conditions today that he's giving us this other pattern. These Shapiro-Kaiser type storms often give us extremely vicious windstorms. You tend to get very, very strong winds in this region of a storm of this type. So when we get extremely strong windstorms, they're very often of this type. The main difference between them is that the Norwegian model has a dominant cold front and somewhat of a non-event warm front, okay? Whereas the other extreme of the paradigm has a kind of non-event cold front and a very, very strong warm front. Both the paradigms, everything doesn't follow exactly these patterns. Each cyclone is unique and looks with elements of these sorts of things. But there does tend to be in most cyclones either a dominant warm front or a dominant cold front, and it depends on features of the larger scale flow in which these things form, which are the two they produce. But anyway, that's kind of showing you the life cycle. But in order for this to happen, what causes this to happen? Well, what causes this evolution is, of course, conditions in the upper atmosphere that generate the right amount of vertical motion, in other words, divergence aloft. So if we go to, oops, this one again, and go backwards, so to the region, to the time when this one was growing. So this is the time when this depression started to grow. In this case, whoops, it's a bit off the chart there, but you can see clearly in this region, we're in this region of where we're in this southwesterly flow downstream of a trough, and that's where you tend to get the growth of the cyclones. Okay. To better understand that, or to get a different handle to what I've shown before, I'm going to take you through, introduce you to the ideas of vorticity. Vorticity is really important when it comes to understanding atmospheric dynamics. It's also, for physics students, it's an insight into the way fluids move, and so it's something that is of general value. And a course on dynamical meteorology wouldn't be complete without at least mentioning vorticity. So what is it? Well, vorticity is simply defined by the curl of the velocity vector. Okay, that's a vector, that's a vector. And we can, if we want to, write all this lot out. These are separate components. It's not particularly valuable to write all this down, because in what I'm going to talk about, because I'm concentrating on the synoptic scale here, I'm going to confine my attention to the vertical component of vorticity. So I'm going to put a Z there for the time being. This is a scalar. Obviously, it's one component of vorticity, and from the Cartesian definition, dV dx minus du dy. Okay, so that's what it is. And sometimes we do use the Cartesian version, but it's not particularly easy to visualize what vorticity is just by looking at this kind of thing. It's clearly so we can kind of pick up one nature of it. V is velocity in the north-south direction, so it's the variation of that in the other direction. So the variation of this component in that direction minus the variation of this in the north-south direction. So somewhere in there is a suggestion that we're talking about some kind of shear, wind shear. But let's look at it with a bit more pictorial representation. Again, looking in two dimensions. Vorticity is a three-dimensional vector, but we're just looking at one component here. And the idea is that we put a small paddle wheel, this thing here is a paddle wheel, and we put it into the flow. And the idea is, if you dropped a small paddle wheel into the flow, if it turns, if you think it's going to turn, then you've got some vorticity. If it doesn't turn, you don't. And the direction it turns gives you the sign of the vorticity. So here we have wind blowing round, in this case an anticyclone, and in this case a cyclone. So here we have clearly that would make
yes, always suppose the arrow is the same direction.
There is something wrong with this, isn't it? This is correct. I've copied it over and flipped it. That arrow should point in that direction. Even I spotted that one. Thank you. Sorry about that. This one causes the paddle wheel to turn in this clockwise direction. Radius is negative. That's taking up the idea from last time. And the vorticity is negative here. So that would give you negative vorticity. This would ignore the arrow. This would turn the paddle wheel in that direction and would give you positive vorticity, which isn't unreasonable. You'd expect that. But also this idea of shearing. So this is the idea that the velocity changes. They're all going in the same direction, but the velocity is changing as you go up the page, a bit like a jet stream. And so what you would get is the paddle wheel now is being forced more strongly on the bottom side than the top, and so it would rotate in this direction here, and that would rotate in this direction here. So well, it would do that anyway. So for synoptic scale motion, anyway, this is what we do. One of the caveats that I have to introduce here is by concentrating on the Z component, I don't want to give the impression that we can ignore the other components of vorticity. The reason that we concentrate on this component is because on the synoptic scale it's not coupled to the horizontal component. The horizontal components are actually much, much larger than the vertical component. The vertical component of vorticity is of the order of f, it's of the order of 10 to the minus 4th second. But the horizontal components are around 100 times larger. And so, why does it make any sense to talk about the vertical component? Well, it's simply because on these very large scales that we're talking about, 1,000 kilometers, there isn't any way of tilting the horizontal component into the vertical. If you look at smaller scale features, thunderstorms for example, if you've ever seen these diagrams of supercell storms, these enormous thunderstorms that produce tornadoes and things like that and big microbursts, then their dynamics depends completely on the tilting of horizontal vorticity to the vertical. So on that scale, and we're talking of scales of kilometers, then this the coupling is very strong between vertical and horizontal. But on the very large scale, it's not. So that's why we're able to take a simple approach to looking at vorticity. And again, to visualize it even further, and to take this idea of curvature and shear, it's traditional to use a system called natural coordinates, so rather than Cartesian coordinates, which are fixed in space. These are kind of Lagrangian coordinates. So here's a streamline, there's the velocity u. S is an x-axis type coordinate along the flow, and then is a y-axis perpendicular to the flow. And you can in fact define a z as well, which would be a vector b if you wanted to do this in 3 dimensions. You can in some cases do that. The value of this is that when we express the vorticity in this coordinate system, we can see the 2 components here as shear and rotational, and they're separated. So here we have the rotational component is just u divided by the radius of curvature. Radius of curvature is positive for cyclonic and negative for anticyclonic. And this is the shear vorticity minus du by dn. And so, and we get just the sum of the two. So now there's no, these two components interchange very freely as the m moves along. So you don't have sort of this to the exclusion of that. In reality, the two swap from one to the other. So we can either use the Cartesian form or this form, depending on which is most suitable for the problem. If we're trying to write a computer program to calculate vorticity, then obviously the Cartesian form is much easier to use. But if you're trying to think conceptually, this form is easiest to use. We will continue with thinking conceptually. And probably the most important concept in thinking about vortex dynamics is this concept of vortex stretching. This diagram, even if you don't understand anything else in the lecture, this diagram is key to understanding how the dynamics of vorticity works. So I'm going to have several nibbles at this diagram. Okay, so for a start, I'm going to make a series of outrageous assumptions and derive a very simple equation, but then we'll revisit it and put fewer assumptions in. Okay, so a column of air, but this is very special air. This air is incompressible. Now, we've met the concept of air as incompressible in the past, so it's not, because obviously if you work in pressure coordinates, that's what you find. So it's not as ludicrous an assumption as it sounds. And the idea is that you've got a disk of air, and it transforms its shape from short and thick to long and thick. Short and back again. So you have this transformation like this. So the vorticity is not conserved. What is conserved? Well, what will be conserved here? Well, two things are conserved. One is clearly the mass of the air parcel has to be conserved. And if we're making an assumption that it's incompressible, its volume will also be conserved. Okay? So the first thing that I'm assuming in this simple calculation is conservation of volume. And the other is conservation of angular momentum. So we're assuming there are no couples acting on this, and this is just a distortion of this parcel of air as it moves, and it's not being acted on by torques. A further assumption, which is done for the purpose of simplicity, is to assume solid body rotation. What does solid body rotation mean? Well, it means that inside, so if I look at the distance away from the axis, and u being the speed with which the point is moving, u is equal to the distance r times the angular velocity omega. So u equals r omega is what is meant by solid body rotation, and that's what you get. Now, obviously, fluids don't generally rotate as solid bodies, but bear with me. This as I say, has several phases to this. U equals r omega, and therefore we can calculate u over r, which is just omega. The n vector, given that I've drawn this, the parcel is rotating, the thing is rotating like that, and so the n vector points in towards the axis. And so obviously the u value increases as you go out from the axis, and so du by dn is negative just because n points towards the axis. And so that's negative, and so this minus du dn is obviously positive. You have two omegas here. And so the vorticity, using this formulation, is basically just related to the angular velocity. Well, that's not really surprising, since we've imposed solid body rotation on this thing, so clearly the vorticity and the angular velocity are going to be one and the same. So there's a factor of 2, well, so what? Okay, so let's now just note that there's a factor of 2 there, and then we just calculate the angular momentum. So this is a fairly simple calculation. It's just the angular momentum, mass, velocity, distance. That's the definition of angular velocity. Here I'm using density. and obviously integrated over the volume of this cylinder. Okay, we want to use cylindrical coordinates to do this, since we are dealing with cylinders. And so the volume is h, and then we've got this r d theta from the element in cylindrical coordinates. The omega r squared comes from here, u equals r omega. And then we just keep on integrating this. We end up with an integral of r cubed, and we end up with an r to the fourth. Okay, so that's the angular momentum about the z-axis. But the other thing that's conserved is the volume. The volume is just the base times height, the area of the base times the height, so pi r squared h. So we can get rid of the r in there using that, and we end up with the angular momentum, which turns out to be density times the volume squared divided by 2 pi times this ratio, and this is the key thing here, the ratio of the angular velocity to the depth. Well, okay, that's pretty obvious. If you take a short fat thing and compress it into a long thin thing, it will spin up. That's exactly what ice skaters do. So this is an ice skater model, if you like, of the atmosphere. So here's our physicist's idea of an ice skater. Throws her arms in, puts them above her head, and she gets into a tight spin. So we've all seen ice skaters doing this type of thing. But the point is that because we can identify omega with vorticity in this case, the vorticity is proportional to the depth of the column. That's what we're really saying here. Vortex stretching an air column increases omega and therefore increases the vorticity. To take this further, okay, so this is kind of very basic, and what's now going to happen is I'm going to get to the same place using rather more equations, okay, and putting obviously fewer assumptions in here. And I'm going to get to a concept of something called potential vorticity. And this is going to look like essentially the conservation of potential vorticity. If you've heard about potential vorticity, some of you have, that's basically what this is showing, but of course we haven't really addressed the full problem at this stage. So what can we actually do? Well, what we have to do next is to roll up our sleeves and say, well, all right then, that was all very well, but we made some pretty drastic assumptions in there that we probably can't push too far. Let's go back to the momentum equations. So these are the momentum equations. Now, I'm not going to go through this in fine detail. You've got the maths on the sheet that I've given you, so you can go through it yourselves, and it's not the kind of thing you can follow easily in a lecture anyway, so if you can't really follow it, then you've got to sit down and go through the handout. But it's not particularly difficult. This is just the full Lagrangian d by dt of the u component, and this is the v component. So here's essentially u dt is minus grad phi plus fk cross u, and this is the Coriolis component. So this is what you get when you write these things out as components. And omega, of course, is the vertical velocity and pressure coordinates as before. Now we want the vorticity, and now it's convenient to use the Cartesian form of the vorticity. And to do that, we just differentiate the first one by x and the second one by y. And you can't do this in your head because you end up with that. Oh dear, lots of terms, but anyway. It's just algebra. You just go through and tidy these terms up. One of the things you can do here is spot that you've got a partial d by dt, u d by dx, v d by dy, omega d by dp. So all of that lot collapses down into a full d by dt, a full of the vorticity. So that's very good. We've also got a v df by dy over here, which cunningly reappears as a rate of change of f following a parcel, because f doesn't vary with time, it does vary with latitude. So as far as a parcel of air is concerned, which moves around, it can experience different values of f. the VDF minus VUDY is clearly vorticity again. We can write the horizontal divergence, which we met before. That's the definition of the horizontal divergence. And so all of this mess collapses into this thing here. So first of all, VDF dy, that's E zeta, and there's an F over here as well coming from those two terms. There's a zeta plus F du, and then there's a load of terms out over here. Well, first of all, we have a vorticity equation, but the term that the term that we seem to be finding in the equation is this. It's the vorticity zeta plus F. So it seems as though the quantity that we should be dealing with in the atmosphere is not the actual curl of the velocity in local coordinates, but we should also add on the rotation due to the rotation of the Earth. So there's a vorticity coming in through the rotation of the Earth, and it turns out to be this F that we've met before. So F isn't just the Coriolis parameter, it now turns out to be the planetary vorticity. So it actually manages to you get two things for one, 2 for 1 here, so that's all good stuff. It's nice when you don't need new symbols. But that's the point. And when obviously the Earth is rotating, and vorticity is a measure of rotation, and so it's not surprising that there's some term somewhere coming from what the Earth is doing. And in that sense, that's how it comes about. So essentially, we've been through the momentum equation, and we've ended up here. Now we've also got, so we've got 3 terms here, or 3 sets of terms. This is obviously the rate of change of absolute vorticity, which is what I'm going to call this combination. We have a term that's related to the divergence of the flow. So now we can see an intimate link between vorticity and divergence. And then we've got these terms here. Now these actually are tilting terms. These are the terms that apply. Like I said, if you're looking at thunderstorms, then tilting is very, very important. Okay, there are frictional terms that come into the equations there as well, which I haven't included here. But the momentum equations I started off with would be valid at the scale of a thunderstorm. It's just that we need to add friction. What do these terms do then? They tilt vorticity from the horizontal to the vertical. So the rate of change of this component has a term depending on the stretching or the compressing, in other words the divergence, and it's got sources from the other components. Okay, so we call that the absolute vorticity, and so we need another term for the vorticity itself, which is relative vorticity. So I'm going to use, so if I'm just using that symbol, then it means a relative vorticity. The tilting terms, okay, like I said, on the large scale, the tilting term is very small. There's no mechanism for doing this tilt, and so we don't need to consider them. So on a very large scale, we get this equation here, which is the barotropic vorticity equation. This is barotropic, just means no horizontal temperature gradients. Now, the reason we call it that is because there's a thing here, dV by dP and du by dP. What's that? That's the rate of change of wind with P, with the vertical. That's rate of change of wind in the vertical. We found out last time round, the thermal wind equation, that is related to horizontal temperature gradients. So where you have horizontal temperature gradients, these terms come in. And so at fronts, where we do have horizontal temperature gradients, these terms can matter. But on the larger scale, away from fronts, grad T is small, and so and that's what barotropic means. It just means there's no horizontal temperature gradient. So barotropic vorticity equation basically means vorticity equation throwing out the terms that are dependent on the horizontal temperature gradient, which is the tilting terms here. The opposite, by the way, is baroclinic, and fronts are sometimes called baroclinic zones. Okay, so all to show that we're very good at speaking Greek, as usual in this subject. Okay, so back to here. So and so there's our barotropic equation, vorticity equation again. That's just taken from the Word document, and throwing those terms on the right away, we end up with this equation here. So what can we do with this? Well, what we do with this is we can develop it a little bit further. That's the rate of change of absolute vorticity related to divergence. And the way in which we develop this is to change it into this concept of potential vorticity. Now here's the diagram again. This is the same diagram I started off with. And last time round I made a load of assumptions about incompressibility and so on. But I'm now taking a different tack to this same equation. I'm using this form of the equation. Remember that divergence is always, in this field now, is always in the divergence of the horizontal components, because the pressure coordinates, the three-dimensional divergence vector is always 0. So again, we have, this time we're talking about the depth in pressure of this this cylinder. Last time around I was talking about height, but it's more sensible to use pressure. Okay, because we're working in pressure coordinates. And PT is the pressure at the top, and PB is the pressure at the bottom of this column, and then delta P is the depth of the column. Okay, that's the geometry. Let's apply this barotropic vorticity equation to the column. Well, first of all, we can note that because the three-dimensional divergence is 0, we can replace the horizontal divergence minus the horizontal divergence by essentially the vertical divergence. This is d omega by dp. In other words, horizontal divergence plus d omega by dp equals 0 is an expression of three-dimensional divergence. So we've got to here. So that's quite good. This is vertical stretching. Obviously, d omega by dp. If that's omega there. If they differ, then the column will either be stretched or squashed. Let's define delta P is pt minus pb. The way I've defined it, clearly delta P will be negative, but never mind. If we differentiate it, then it has to be the differential d by dt of that must be d by dt of these two things, and obviously they are omega by the definition of d by dt of pressure. So that's the difference in omega at the top minus omega at the bottom. And again, this can be expressed as d omega by dp times delta p, the same kind of thing. So here's our d omega by dp here, and so basically it's the rate of change of this. So d omega by dp times delta p is basically the rate of change of delta p. So d omega by dp is 1 upon delta p by dt. That's sensible enough. That's just basically stretching. We now substitute this in the vorticity equation, which is this equation, and we have d by dt of this minus, so this is this term here, zeta plus f, there's our term here, over delta p, d dt delta p is equal to 0. And it's very simple to show. Just divide this equation through by 1 over, just divide it by delta p, 1 over delta p, 1 over delta p squared, and we can quickly show that this expression is 0. So the rate of change of vorticity, the absolute vorticity divided by the depth, is equal to 0. This expression inside the bracket is the potential vorticity, or it is one version of the potential vorticity. But again, what you see is exactly the same as this very simple model that I used earlier with the incompressible fluid. You just find that the ratio of the vorticity to the depth is conserved. Now the value of that, of course, is that it's relatively easy to look at a chart and see how the vorticity of a fluid is changing. Just as an aside, so the quantity zeta plus F on delta P is actually called the Rossby form of potential vorticity. This stuff was worked out, it's actually a long time ago. It was in the end of the 1930s and during the 1940s that this stuff was worked out. And in fact, in 1942, a guy called Hans Hertel came up with a different form of the PD equation, which has become almost the bedrock of modern meteorology in its more comprehensive form. There's no scaling going into this equation. I don't want you to learn that off pat. I'm just showing you. It's one of these extraordinary things where you can actually get from F equals ma basically to this equation here. So it's even got friction in it. So there's curl of friction. So this is showing that for this is the way that potential vorticity is expressed in this form. This time it takes account of all three components. So this is a vector. That's the three-dimensional curl of the velocity. So this is the gradient of potential temperature, which normally is upwards, and that's the rotation rate of the Earth. And so basically it's saying that the only things that can change this quantity are rate of change of potential temperature. This is for a parcel, this is diabatic heating basically, and so condensation, evaporation, radiation, those are the main things that do that, and then thermal friction, so that if you're at the surface, obviously there's another term that comes into the equation. But that's, I mean, it's if you're interested, then I've put the derivation on the web page, but I do not expect you to learn it. So the key thing to remember is this diagram. And if we go back and look at some of these charts that I showed, so any of them will do. So if we look at this chart here, what are we seeing? Well, it's fairly simple to examine a chart like this and say, well, okay, what is this? What's the vorticity in this area here? Well, we have a rotation. The wind starts off going this way and it rotates. Well, it's clearly rotating in a clockwise fashion, and so that's anticyclonic. And so this is a minimum in vorticity, if you like. There would be a maximum in vorticity down here, and you've got another maximum minimum. And so just by looking at these troughs and ridges, you can argue, well, okay, here we have air flowing from here to here. What's happening? Well, vorticity is increasing because obviously negative to positive vorticity as we go from here to here. What would you expect to see? Well, you'd expect to see, therefore, increase in vorticity, therefore stretching of the air parcel, and therefore, in some way, you'd expect to see stretching of the air parcel. Well, what does that do? It would push the air. Well, it's up and down, really, wouldn't you? You'd expect to see both. Tomorrow I'm going to take this idea a bit further and show you that actually it doesn't mean that. It actually means that it would push the air downwards, because the alternative would be to push the stratosphere upwards, and the stratosphere resists being pushed upwards. You'd also say, well, hang on, you talked about vorticity here, you haven't talked about F, and as you go from here to here, you're going to lower latitude, so obviously there's going to be a decrease in F. So that'll cancel out this change in the vorticity, perhaps. So we need to address that as well, which I'll do tomorrow as I give you the final lecture in this set of dynamics lectures. Okay, so I'll finish at that point. Any questions? Okay, thank you. So I'll see you tomorrow then. Which one of you's got the clicker thing? Oh, you. Yeah, so you should be able to scan it. Thank you.
我弄了一会儿，反正我晚了50分钟，就晚了5分钟。我也没变，想了想就行了，但是它是没变。
这是选址。这是有一杯做的。